let's get to physical properties, because this is one of the coolest videos I've ever seen, and I definitely want to share it with you guys. So soil structure, this is a physical property now. Just like soil texture is a physical property. This is just some soils, the way they develop, they form different structures, which is highlighted here in the picture. So if you look at these, if you have something like a single grain or massive or platy, for example, and you poured water on that type of soil, this is a question to you now, is that what, relative to these other structures like blocky or prismatic, which one is going to allow water to penetrate faster? All right, granular would be, I forget the way I phrased it, but it would be much slower for the platy, massive, or the single grain, because these are very small particles. These others have a lot larger gaps in their pore space is what they call it. The percent of area that's filled up by pockets of air as opposed to soil particles. But just the physical orientation of how the soil is will determine if that soil can drain. Now in garden soils, typically we're tilling pretty heavily, much to my chagrin. I'm a big no-till advocate, at least for crop production. And we could have that debate at the end, which might be interesting. Because you can no-till gardens, but you might take a hit in terms of yield. Anyway, you're typically mixing the soil up so much and you're adding so much compost that it's altering the physical structure to be more like single grain. Now, if you only had clay soil, you'd be dead in the water, literally. You'd just be flooding your soil, nothing would get through. That's why they coat the bottom of the lagoons with that thick clay. But you guys are not just tilling up clay and breaking tiller tines all summer. You're usually putting in compost, and compost creates that intermediary particle that does not adhere like clay, and it doesn't improve physical structure, so to speak, but it improves porosity. When I think of structure, I think of aggregation of soil into what would look like blocky. And if that needs more clarification, just ask. But this type, so if I just had massive chunks of soil like this blocky or prismatic, there's very large gaps versus the single grain, which has very little gaps or small gaps. That affects how your soil can actually hold on to water. So when I pour water, say on a houseplant, for example, I'm counting on that soil holding the water so I don't just flood my kitchen counter every time I water the plant. The soil is holding on to it, but how is it doing that? Because if I overwater, certainly that water comes out the bottom. And so there's several things going on there. There's the torosity, or how torturous it is for that water to make it through, but there's also how close are those pores. There's something called adhesive and cohesive forces with molecules. Cohesive are attraction between molecules that are the same, so water attracted to water molecules. And you can see that force in effect if you overfill your water just slightly enough and you get it eye level with the cup, you'll see it crowning on the top of the cup without spilling over. That's because the water is literally holding itself together with surface tension because of these cohesive forces. But there's also called adhesive forces. Now, this is part of why I spent such a long time on talking about the charge of soil and cation exchange capacity, because soil, because it has that negative, because it has any charge at all, can attract water loosely. It's not like it's not necessarily, again, like a covalent bond, but it can hold on electrostatically enough that it can resist gravity's pull of that water going below. So how do you get the best of both worlds? If you have particles really close together, you provide water a lot of adhesive areas to grab onto, but then the water is close enough to itself that it can be cohesive with itself and resist gravity. So you have both forces opposing gravity at that point. And that's how water is staying in an otherwise open system to air going back and forth from just simply draining out the bottom. Now the video I'm going to show is just, it really hits it home. It's going to be about 5-6 minutes, but I think it's 5 to 6 minutes that you'll enjoy. I really get a kick out of it. And the question is, why does a screwdriver go into wet soil easily and with difficulty in dry soil? The reason that is because when you lubricate soil, especially clay or other soils, you give it a fluid network, so to speak, or fluid system that it can now move in. So instead of acting strictly as a solid, you somewhat liquefied it, and it allows the particles to move in that fluid and reshape themselves to get out of the way. When you dry soil down, it solidifies the structure that's already there, and there's an intense amount of resistance there when you talk about the different types of soil. So sand, it's still relatively easy to push through, but clay, like that platy structure, if it starts to dry in a platy fashion, you're resisting millions of these clay particles pushing back against you at right angles. And so it's very hard to do that unless you lubricate the soil and give it a way to kind of, for lack of a better term, just kind of swim or push out of the way. Not a very scientific way to answer that, but that's basically what's happening. So let's watch the video for about 5-6 minutes. It's a good one. It's a goodie. There's probably an advertisement, so just bear with me. This is YouTube we're talking about. Come on, man.
Water movement in the soil is determined by the distribution.
I'm going to skip through some of this.
This video will show the basic principles governing water flows. In these demonstrations, soil is held between glass plates so that you can watch what happens as the soil is wetted. The glass plates are 30 centimeters high and 60 centimeters wide, with about 2.5 centimeters of space between for soil. Think of this model as representing a vertical cross-section through the soil. Thanks to time-lapse photographic processes, actions that would require many hours in nature will be observable in just a few minutes. Using a motion picture camera, single pictures are taken every second as the water moves into the soil. The completed motion picture film is then projected and speeded up 25 times. Because water movement is usually very rapid when water is first applied and very slow at later times, the speed-up factor might change during a sequence. This will be indicated on the screen. The soil used is an air-dried loam, which has been passed through a fine screen. Sand, clay, and aggregates are used to simulate non-uniform bodies in a soil profile. Water will be added in a furrow with a funnel connected to a tap, which keeps the water level at any desired depth. Before the sequences using time-lapse photography, here is a demonstration that illustrates the principle of capillarity. This principle is involved when water moves into dry porous materials. Liquid is pulled because of the attraction of solid mineral surfaces for water, adhesion, and the attraction of water molecules for each other, cohesion. Adhesive and cohesive forces are responsible for moving water upward against the downward force of gravity. In this demonstration, water rises between two closely spaced plastic plates because of the adhesive forces between plastic and water and cohesive forces between water molecules. The height of rise is greatest when the plastic plates are pinched tightly together. The pressure in the water above the free water surface in the container is less than atmospheric pressure. This is called tension.
So this was what I was talking about when you have single grain close together versus if you had, say, like aggregates that may have small pore space within the aggregate, but between aggregates themselves, there's larger gaps. You would expect less resistance against gravity's force. And so that if you have a clay soil, you have very tight particles, higher resistance against soil, and clearly that can be shown when clay soils take forever to dry out, it seems like. And it also takes forever to get the water into the soil because you're going through such little tortuous paths to enter the soil. So hopefully that clarifies that point. Let's keep going with the video.
The higher water rises, the greater the internal tension. Now to the models and time-lapse pictures. Before analyzing the problems of stratification, it is important to illustrate differences among uniform soils with respect to their ability to transmit and retain water. Note that the depth of penetration at any given time is greatest for the sandy loam, which has the largest pores, and least for the clay loam, which has the finest pores. The finer the pores, the more the rate of water flow is restricted. Retention of water after the source is removed is greatest in a clay loam, which has the finest pores, and least in a sandy loam. Despite this, however, the net useful storage is greatest in a clay loam and least in a sandy loam. Although sandy loam retains less useful water than does the clay loam, it is a good soil in an irrigated area where lack of water holding capacity can be compensated by irrigation. The infiltration properties are generally good. Clay loams, on the other hand, are often difficult to irrigate because of low infiltration rates. In dry climates where there is no irrigation, and sandy loam would not hold enough water to carry agricultural plants through the growing season, a clay loam, by contrast, would retain more water over a longer period of time. Hence, dryland farming on fine-textured soils is practical. The rates at which water would enter the soil is an important factor to consider when designing an irrigation system or when deciding on cultural practices for use in erosion control.
All right, now to the good stuff, hopefully. Okay, why I'm bringing this up is because when we modify gardens, we have the ability to literally modify them, especially if we have a raised bed, to do whatever we want to them. Now, when I was probing around in the backyard farmer garden on campus, I got the probe about 12 inches down, and it was really, really fluffy. A lot of compost and organic matter in there. So water would just race through that soil. But by the time my probe got 12 inches down, it hit a solid sand layer. I was shocked. I did not expect that. I expected to hit, I guess, what the surrounding soil would be, which is like a crete silt loam. And so in this case, the backyard farmer has a very porous soil, which is the opposite of clay. But keep that in mind when you're watching these next few demonstrations. So loam has finer, smaller pores. It retains more water, takes longer to go in than sand. So you would expect more cohesive and adhesive forces taking place in the loam. And so this is a question now to everybody. What do you think is going to happen when that water that is in the loam reaches that sand layer? Is it going to go through that sand layer immediately, or is it going to have to fill the loam layer first before it can then enter into the sand? What do you guys think? Goes right through. Okay, yeah, for Sydney, instead of not just through the sand layer, but will it go from the loam straight through the sand and then out? Once it hits the sand, it'll sprout out in the sand. Okay. A few more guesses and then we'll reveal the results. Everybody's done guessing, I guess. All right, let's hit it.
Watch as the water moves out from an irrigation furrow. Note that the movement outward is almost as great as that downward. This is added evidence that the force responsible for this type of water movement is mainly due not to gravitation, but to the attraction of solid surfaces. As the soil becomes wetter and wetter, however, gravitation plays a stronger role, and if the soil becomes completely saturated, then gravitational forces predominate. The horizontal layer you see is coarse sand. One of the important principles of unsaturated flow is described as you witness what happens as the wetting front encounters this layer of coarse sand. The pores in the soil are many times smaller than those between sand grains. Water is held in these small pores by large adhesive and cohesive forces. The pores in the soil are like the pores in a piece of blotting paper used.
All right, I'm going to speed up and go to another one. So the first time I saw that, I had to think about it. I just did not think about it. It just didn't make sense. Now, they kind of inverted it. Now they put a clay layer below a loam layer. What do you think is going to happen? And hint, A to the E to the B to the C horizon might give you some clues. Should go through, the panhandle says. Anybody else? All right.
Otherwise uniform
Gary,
soil.
you're right.
This clay layer is similar to a clay pan or any type of layer in which the pores are extremely fine compared to the pores in the overlying soil. These layers often restrict root and depths of plants and are particularly known for the trouble they cause in preventing downward penetration of water. When excess water is added to the soil, water tables are often built up over such layers. If they occur at shallow depth, water tables often rise above the land surface during wet seasons, imposing serious limitations on agricultural use. Despite the fact that a clay pan hinders downward movement of water, it does absorb water readily as the soil above is wetted. Observe the wetting front as it moves into the clay pan. The pores in the clay are much finer than those in the overlying soil, so they can pull water from the soil. Water tables are not built up over clay pans because of the inability of water to enter them. Instead, water tables result from slow transmission of water. The resistance to water flow in these extremely fine pores of layers like these is sufficiently great that even over periods of weeks and months.
I'm going to end it there. So I encourage you to go to the rest of the video. It's really neat. They talk about different things, different types of layers, channels from like earthworms or rodents, and what happens when water interacts with aggregates. I just find it to be a really good resource. And kind of challenges my intuition about some things. For example, it should go through the clay, but just how much clay, I guess, depends. And so these things this is something we need to think about. So if you put your raised bed over solid clay, you still have to think about how are you going to deal with water in that situation, because typically it will start to pool up until you're flooding your garden, even if it's a raised bed. So think about the whole profile and the whole system, and if you cannot remediate the whole situation in terms of just by changing what type of soil you have, you may need to add some type of drainage tile to help deal with these issues, or change the way you irrigate. And I'm not an irrigation specialist, but it certainly plays a role in that. And if you can't keep water in your soil, you can't keep nutrient cycling as well, and of course you can't keep your plants growing. So let's move on from that.